Sketches can help you understand and learn equations. In this video, I'll look at voltage equals current times resistance, equivalent to voltage equals current over conductance. We start by representing terms as sketches that explain the term. Voltage can be represented as charges separated by something, space, a membrane, distance. So voltage is the amount of charge difference between two locations. Current is the movement of charge from one direction, from one location to another. Consider an electron that is moving along a wire. That movement of one or more electrons along the wire is a current. Similarly, in biology, we often have channels, and an ion moving through a channel is also a current. So charged particles moving from one location to another is a current. Resistance is how easily the charge moves. So if we have a thin wire, we can easily fit one electron through that at a time, but if it's really thin, that single electron will repel any others trying to move through. So a very thin wire has very high resistance. Similarly, if we have a membrane that has only a single channel in it, only one sodium might fit all the way through that channel at one time. There's high resistance. It's harder to move many through at one time because the sodiums repel each other. We can decrease resistance by making a thicker wire so that multiple electrons can go through side by side. So this is lower and higher. Conductance is just the inverse of resistance. If we had a single channel or a narrow wire, we have low conductance. If we added a second channel, we'd have higher conductance. So this is lower conductance, lower C, and this is higher conductance. We can represent an equation as a sketch. I'll do this top one, voltage, difference in charge between two locations, equals a current, movement of charge, divided by the conductance, which is the number of ways that an ion can move from one location to another. And we could do the same thing for voltage equals current times resistance. We can use these sketches to understand these equations. We change any variable, and then we use sketches to help us understand the outcome. So let's say we double the voltage. So we started with this, and we have a particular current, and a particular conductance. So if we double the voltage, we've got V equals I over C. If we double the voltage, then the only way to have this equation still be true is to double this side of the equation. So if we double the voltage, if the conductance stays the same, this is maybe a membrane and it's just got that number of channels, or it's a wire that's a particular thickness. If we double the voltage, we must also double the current. If we double the voltage difference, then we're going to have more repulsion of sodiums over here, more attraction of them over here, and so they're going to move faster and more easily through the same conductance to get to the other side. We double the voltage. If the conductance stays the same or the resistance stays the same, the current has to double. What if we double the conductance? Well, we have a particular voltage. We've got a current. And let's say we have now doubled the conductance. We've gone from maybe 2 to 4 channels here. Well, if we double the conductance with the same charge difference, there are more ways to get sodium through. So we've doubled the number of ways to get sodium through. We've caused the current to increase. With more sodium coming through, the current is going to increase. If we look at V equals I over C, if we double the conductance and we've kept the voltage the same, the only possible outcome is that we've doubled the current. 2I over 2C equals the same as I over C. What if we decrease the current? So again, we start with our charge difference, that's our voltage. We have a particular conductance. We have a particular current. We want to decrease the current. What could we do? Well, we could cut the voltage in half. If we cut the voltage in half the voltage, then we'd need to cut the current in half for the equation to be true, and that makes sense. If we cut the voltage in half, there's less charge pushing sodiums through. Or we could remove half of the channels. If we remove half the channels, we have decreased the conductance, increased resistance. If we remove half of the channels, then we should go to 1/2 of the current. Now, just watching me do these will not help you understand these equations really well unless you do the same thing yourself. So I'd recommend you do these same exercises, but also do some of your own in order to practice.